Okay, hi guys. So in this lecture, we'll be first starting off with cyclic process. Okay, so let's suppose we have a graph, a PV graph. Okay, and this is something like gas first goes from state A to B, then C to D. So from A to B, there is an expansion. B to C, um, the volume gets lowered at constant volume. From C to D, it's a compression, and from D to A, again the volume increases at constant volume. Pressure increases at constant volume. So as U is a state function, so delta U would be 0, hence we can write W plus Q would be equals to 0 in this case. And in AB we can see there is a gas expansion, and from CD we can see that there is a gas compression. Okay, so here it is a negative work done, and here it would be a positive work done. Why? Because we know that SP equals to minus W equals to minus P dV. So as dV is getting dV is positive in this case, so work done would be negative, and in CD dV is negative, hence work done would be positive. Okay, so we can write W total would be equals to work done from A to B plus work done from C to D. And why we are not including work done from B to C or work done from D to A? Because those processes are at constant volume, so value of dV would be 0, hence work done would also be 0. So this would be same as area of rectangle ABCD. Okay, and as it is the whole process is clockwise, so we will be writing negative for the total work done. Okay, this is the sign convention which is followed in cyclic processes. Had it been anti-clockwise, then it would be positive. Okay, so just as in this case, that suppose we have a PV curve in which we have something like this, a process or the gas goes from state A to, so from A to B, then C. So this is the process. So work done total in this case would be work done across A to B, work done across B to C would be 0 because it is at constant volume. Then it would be work done across C to A, and we'll compute this. We take the sign to be negative. As it is anti-clockwise, the sign would be positive, because in clockwise we take total work done as a convention to be negative, and in anti-clockwise cyclic process we take the work done to be positive. Next, let us see polytropic processes. So in polytropic process we have a equation that PV to the power m is constant. Okay, this is a polytropic process. We already know that du equals to dq plus dw. So du can be written as ncvm dt, which would be equals to ncm dt, which is the molar heat capacity, plus dw can be written as minus pdv. Minus pdv. Okay, so from here we can write ncm dt would be equals to ncvm dt plus pdv. Okay, and cm would be equals to cvm dt plus, or rather cvm plus dt and dt get cancelled out, plus p upon n dv upon dt. Okay, so this is, let's say, our first equation. Okay, and now we also know that PV to the power m is constant, and for an ideal gas we can write PV equals to nRT. So just substitute the value of P equals to nRT upon V in the previous equation. So nRT upon V times V to the power m would be equals to constant. From here we can write that, let's say this is some constant K. So KT into V to the power 1 minus m would be some rather this would be or let's do the other way around to simplify the things. We can also show from here, but let's simplify this because we are dealing with two constants if we go by this approach. So suppose we have, as we know that PV equals to nRT, so suppose we have PV to the power m equals to some constant k. So we pick up the value of P from here, which would be kV to the power minus m, and put it in this equation. So it would be kV to the power 1 minus m would be equals to nRT. Okay, and if we take the differential of this in both LHS and RHS, it would be kV to the power 1 minus m would be equals to rather d kV to the power 1 minus m would be equals to d nRT. So from here we can write that it would be k multiplied with 1 minus m v to the power 2 minus m dv would be equals to nr dt. Okay, so from here we will get the value of dv upon dt by simplifying this. So it would be nr divided by k 1 minus m v to the power 2 minus m. So this would be the value of dv by dt. So put this value of dv by dt from equation number 2 into equation number 1. Put the value of dv by dt here. So we would be getting Cm would be equals to Cvm plus this is P upon N. So it would be P upon N times dv by dt. dv by dt is nr divided by k1 minus m v to the power 2 minus m. N and n gets cancelled out, and we already know that p v to the power m is constant k. We have already assumed it. So p can be written as k times v to the power minus m. So Cm would be equals to Cvm plus p can be written as k v to the power minus m times r, which was already present here, divided by k 1 minus m v to the power 2 minus m. So here k and k gets cutted out, and then we would be having, rather it would be, I think we have done some mistake here. So d of 1 minus m would be, so d of x to the power n is n x n minus 1. Okay, so d of v to the power 1 minus m would be, 1 minus m is n, so 1 minus m times x to the power 1 minus m minus 1. So it would be minus m only, not 2 minus 1. It would be minus 1 only. Okay, so just a silly mistake here. So now it would be v to the power minus m, not 2 minus m. Okay, similarly correcting here and correcting here. So now this is v to the power minus m. So minus v to the power minus m and v to the power minus m gets cut out. So finally we have Cm equals to Cvm plus r divided by 1 minus m. Okay, so this is molar heat capacity in relation to molar heat capacity at constant volume plus r divided by 1 upon 1 minus m. So we can also write that Cm minus Cvm would be equals to r upon 1 minus m. So with this we come to the end of this lecture. In the next lecture we will be seeing some examples on the same. So till then, good luck and goodbye.